So welcome to today's SCA webinar with Jim Brinicke on atypical hydrocarbon water contacts, perched water, and tilted hydrocarbon water contacts. Before I introduce Jim, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature. We'll cover the Q&A at the end of the presentation, and you will be anonymous. So this is the presentation introduction with Jim Brinicke. Jim is a graduate of Augustana College with a master's from University of Illinois. He started his career with Shell and worked in various subsidiaries around the world. He then joined Subsurface Consultants and Associates as a consultant geologist. Additionally, he worked as a technical manager, a vice president of geology engineering, and treasurer for SCA. Then he joined BP's Deepwater Gulf of Mexico production organization. Jim has a wide range of experience. He's worked in both onshore and offshore in a variety of different international locations. He's contributed discoveries around the world, and he's recently co-authored the new book, new edition of the Applied Subsurface Geologic Mapping book that's used as the text for the course that Jim teaches for SCA, Applied Subsurface Geologic Mapping. He also teaches QA/QC skills for subsurface maps. So here are the dates in which the Applied Subsurface Geologic Mapping class is offered towards the end of this year and next. So plan to attend one of these public classes or invite SCA to offer this course in-house at your location. We do provide discounts for those of you who are in career transition, and we have a number of other training courses that are available for you. Of course, in addition to training, SCA also offers consulting, direct hire, projects and studies, and additional services. So without further ado, I'm going to give the presentation rights to Jim. And Jim, please start your presentation.
Thank you, Susan, and thanks to SCA for giving me the opportunity to make this presentation. I was fortunate enough to have Dick Bishke ask me to participate in the writing of the third edition of the Applied Subsurface Geologic Mapping textbook. And I added a couple of topics to the textbook. But because the textbook is quite long, it's over 900 pages, the discussion in the text was very brief. So today is going to give me an opportunity to go into a little bit more depth on a couple of the new topics that are mentioned in the third edition of the Applied Subsurface Geologic Mapping textbook. And those two topics deal with atypical hydrocarbon water contacts, specifically contacts related to perched water and to tilted hydrocarbon water contacts. So let's begin by talking about perched water. And I'll start with my definition of perched water. Perched water is formation water that is trapped in closed flows on the base of the reservoir above the field hydrocarbon water contact in an edgewater hydrocarbon accumulation. And let me remind you of what an edgewater hydrocarbon accumulation is by looking at a couple of maps and a cross-section. We'll start off with a top-of-reservoir structure map. On an anticline, we see that we have an oil-water contact several hundred feet below the crest of the structure. And if we look at the base-of-reservoir structure map, we see that the oil-water contact intersects the base-of-reservoir structure map 300 and some feet below the crest of the structure. So part of the structure, at least, is full to base with oil. If we look at our cross-section AA prime, in a very extreme vertical exaggeration. We see the oil-water contact. We see that most of the center of the anticline is filled with oil to the base of the reservoir. And we have water wedges on the side of the structure. And this is called an Edgewater reservoir because if you start producing the reservoir, water encroaches into the reservoir from the edges of the reservoir because much of the center of the anticline has no water directly underlying the oil. We'll contrast that with an Edgewater oil reservoir that might have perched water in it. Here is a very similar structure map on the top of the reservoir. The only difference is now we have mapped 4 small closed lows within the overall anticlinal structure. And this is a tip that you could have perched water in this accumulation. If we look at the base of reservoir structure map, we see our 4 closed lows on the base of the reservoir. And these are areas where perched water can be trapped. If we look at our cross-section AA prime again, we see our anticline that is largely filled with oil. But here in one of our closed lows that is crossed by this line of section, we have trapped water. So what happened in the charging of this anticline is oil began to accumulate in the crest of the anticline, and it displaced formation water out of the crest of the anticline. As the anticline continued to fill with oil, the oil came down to a level right about here, at which point the oil could no longer displace formation water out of this closed low. The lower density oil couldn't force the higher density water up over this sill and allow it to flow down into the regional aquifer. So that water became trapped or perched above the field oil-water contact. Here is another example from Weber's 1995 publication on perched water. And here we see a fault propagation fold where there is water trapped in a closed low on the frontal limb of this anticline. And we see that the gas extends much further down dip to the field, the gas-water contact on the back limb of the anticline. So this is another type of structure where you can find perched water. A third example is from the Ram Powell field. This is the N reservoir in that field, and the N reservoir is a series of an amalgamated channel sands that were cut into some slope shales. And these channel sands developed some closed lows and trapped water within those closed lows. I'll caution you that in an example like this, mapping the base of the reservoir can be very difficult. You frequently don't have the seismic resolution to resolve these individual channel sands, and you don't have enough well control to contour out these closed lows. So you have to infer the closed lows if you encounter perched water. Here is another example from Grain Field in the North Sea. Here we have a very nice thick sandstone, 2 wells that intersected the sand at the same depth, but the G39 well encountered water 20 meters above the field oil-water contact. if we look at a structure map on the base of this reservoir, we see that the G39 well intersected the base of reservoir in a closed low. There's a closed low here, there's another closed low there, maybe a couple more. So that explains why we had water trapped in these closed lows above the field oil-water contact. The importance of perched water is threefold. First of all, if you encounter it early in the exploration or appraisal phase, you can significantly underestimate the amount of hydrocarbons in place. Once you have appraised and start to develop an accumulation, you may overestimate the hydrocarbons in place, but usually this is relatively minor. Third, the presence of perched water and recognizing perched water can impact your perforation placement in completions, and we'll go over each of these three with some examples. Here's our faulted anticline again, and I have inserted a well number 2 that drilled down the back limb of the anticline. And on the right-hand side of this figure, I have put in the pressure data that you would expect to see from a well like well number 2. At the gas-water contact, the pressure in the gas and the pressure in the water have to be equal, because a hydrocarbon-water contact cannot hold a pressure differential. So here we have the pressure in the gas accumulation and the pressure in the aquifer. They're equal, and the pressure in the gas phase is controlled by the pressure in the aquifer at the gas-water contact. The gradient in the gas phase is controlled by the in-situ density of the gas in the reservoir, and the gradient in the aquifer is controlled by the in-situ density of the formation water in the aquifer. So in this case, we have drilled the field gas-water contact. We have a pretty good idea of what the in-place volume of our structure is. But suppose we drilled well number 1 before we drilled well number 2. And here is well number 1 that drills the frontal limb of this fault propagation anticline. In this case, we encounter a gas-water contact much higher on structure. And if this is the field gas-water contact, we have a very small accumulation, which may very well not be economic to develop. If we look at our pressure data, once again, we see the gas pressures are falling on the same trend line as all of the other gas pressures from well number 2. The water pressure in the perched water leg lie on a gradient that is reflecting the density of the water in the perched water leg. At the contact, the pressure in the water and the pressure in the gas are the same, just as in the field contact. In this case, however, the pressure in the aquifer is controlled by the pressure in the gas phase at the perched water contact, as opposed to being the pressure in the gas being controlled by the pressure in the aquifer at the field gas-water contact. So we have a challenge of trying to determine, if we drill well number 1 before well number 2, is this a perched contact or is it the actual field contact? And there are at least 3 ways in which you can do this. If this reservoir has an amplitude signature, you may see that the amplitude extends much further down on the back limb than it extends on the front limb. And this is a clue that you have drilled a perched contact. Now, the front limb of a fault propagation fold is frequently steeper than the back limb. And steeply dipping reservoirs tend not to be as well imaged on seismic data as less steeply dipping reservoirs. In some cases, you don't have the recording devices recording at far enough distances to record steeply dipping events, or you don't process steeply dipping events properly. So the amplitude on the steep dipping limb may not be as well defined as the amplitude on the more gently dipping back limb. But you can tell that the amplitude extends much further down dip, and that tells you probably drilled a perched contact. The second way you can recognize that this is a perched contact and not a field contact is if you know the pressures in the regional aquifer. You'll notice that the pressures in the perched water are much higher at a given depth than the pressures in the regional aquifer. So if you drill into a water beneath gas and you've encountered pressures that are higher than you expect for the regional aquifer, then you may recognize that you have encountered perched water and not the regional contact. The third way that you may be able to recognize that this is perched water is by mapping the base of the reservoir. And if you have a closed low on the base of the reservoir and the closure corresponds with the depth of the contact, then you have a very good indication that you're dealing with a perched contact and not the field contact. So let's look at an actual example of some pressure data. This is from the 8,500 foot sand in Garden Bank's 191 field in the Gulf of Mexico. And here you see a number of wells that have measured pressures in the gas phase in the 8,500 foot sand. And one well encountered perched water, and another couple of wells encountered the field gas water contact. Now, in the third edition of the textbook, I summarized this data into a little graph that looks like this, where you have the gas pressure trend, the perched water trend, the perched water gas water contact, and the field gas water contact with the aquifer pressure trend. Now, in this particular case, the well that encountered perched water was a development well, so the operator already knew where the field gas water contact was and knew that he had perched water. If this had been an early well, the Garden Bank's 191 field, 8,500 foot sand is an amplitude play. So it would have been quite clear from the amplitudes that there was more gas than was indicated by this perched water contact, which is fortunate because the 8,500 foot sand is an amalgamated channel sand, and this is probably an erosional low, which I do not think you would be able to map. So it's a good thing that it was encountered late in the development, and it's an amplitude supported accumulation. We'll go back to our base-of-reservoir structure map from the beginning of this discussion and just point out that the amount of reservoir that has water in it in these perched water areas as opposed to oil in it is relatively minor. So if you aren't able to subtract all of that volume from your oil in place, usually it's a relatively minimal impact on your hydrocarbon in place estimates. So it's something to be aware of, but usually it's not a really major issue. Let's go back and look at our grain field example and think about how we would complete these two wells. I have shown a completion interval for both wells, which goes all the way to the oil-water contact. And let's think about how these two different wells would behave if they came on production. In looking at the well that drilled the aquifer contact, and we have completions, perforations all the way down to the contact, we would expect this well to have a rapidly increasing water cut, assuming we have a reasonable water drive in the reservoir. That's because as you start to produce the oil, water is going to cone up into your perforations, and it is going to produce in your fluid stream. This will result in declining oil production for a couple of reasons. First of all, the amount of fluid produced out of this completion will probably decrease because the average density of the fluid is increasing with the increasing water cut. And therefore, for a constant pressure drop, you're going to have less fluid produced. And then because the water cut is increasing, the percentage of oil in the produced fluid is decreasing, and the two combine for a significant declining oil production. We can contrast that with our completion for the well that encountered perched water. Here we would expect stable, low water cut because there really is no drive in a perched water accumulation. It's too small to have a significant drive, and therefore we would expect stable oil production. So you might want to use a different perforation strategy for a well that encountered perched water than for a well that encountered the field contact. One last comment about perched water before we go on to tilted contacts, and that is that the perched water is really frozen in time. In this cartoon, I've illustrated much lower resistivity in the water, in the perched water, than you have in the field regional aquifer. This would suggest that the chemistry of the water in the aquifer changed over time, and we have frozen more saline water, caught more saline water in the perched water, and then the regional aquifer became less saline over time. So you may see differences in resistivity in the perched water versus the regional aquifer. So that ends the discussion on perched water, and we can now go on to tilted hydrocarbon water contacts. Our understanding of tilted hydrocarbon water contacts really traces back to M. King Hubbard, who wrote a seminal paper on the subject in the AAPG Bulletin in 1953. Most of the time, when you encounter a hydrocarbon water contact, geoscientists and engineers assume that that contact is horizontal. In many cases, at least, that assumption is accurate. The contact is horizontal. If you encounter it at one point in the field, the pre-production contact is going to be the same any place in the field. In some fields, this assumption may not be strictly accurate, but it's close enough that your interpretation will allow you to make good business decisions. There are cases, however, where the assumption that the contact is horizontal is not close to reality, and interpreting the contact as horizontal will cause you to make bad business decisions because you will have a poor subsurface interpretation. And Hubbard recognized that what controlled whether you had a horizontal contact or a tilted contact was the characteristic of the aquifer itself. He recognized two types of aquifers. The first is a hydrostatic aquifer, and the second is a hydrodynamic aquifer. In a hydrostatic aquifer, the aquifer is in pressure equilibrium. The potentiometric surface for this aquifer is horizontal, and as a result of it being in pressure equilibrium, there is no fluid flow in the aquifer. And in a hydrostatic aquifer, you are going to have horizontal hydrocarbon-water contacts. In a hydrodynamic aquifer, however, the aquifer is not in pressure equilibrium. The potentiometric surface is not horizontal, it is inclined. And because there is a lateral pressure gradient in this aquifer, you have fluid flow within the aquifer, and you have tilted hydrocarbon-water contacts. I never knowingly worked a hydrodynamic aquifer in my full-time career. I was aware that there were hydrodynamic aquifers and tilted hydrocarbon-water contacts, but I never knowingly worked a field that had them. And I had the impression that it was the fluid flow that caused the hydrocarbon-water contact to tilt. This belief is incorrect. The lateral pressure gradient causes the aquifer to have fluid flow, and the lateral pressure gradient causes the hydrocarbon-water contact to tilt. So these are two responses to the lateral pressure gradient. It is not a case where the flow in the aquifer tilts the contact. And let me lay out the reasoning behind that. Here is a classic example of a onshore hydrodynamic aquifer from Hubbard's 53 paper. We see here that we have a recharge area where rainfall at high elevations on the edge of the basin infiltrates the aquifer and flows down and through the basin and then up on the other edge of the basin into a discharge area that is at a lower elevation. And the potentiometric surface for this aquifer is a straight line between these two elevations. In looking at this, Hubbard recognized that if you have rainwater, fresh water, that is entering into an aquifer and flowing through it, you have to have a hydrodynamic aquifer. So if you have fresh water in your aquifer, it has to be hydrodynamic. You don't have to measure pressures to know that. If we do look at pressures in this aquifer, in this hydrodynamic aquifer, and we'll look at pressures, this Z distance above the sea level, we see that the pressure at point 0, P0 is higher than the pressure of P1, which is greater than the pressure P2, which is greater than the pressure P3, which is greater than the pressure P4. This is because the hydrostatic head at P0 is greater than the hydrostatic head at P1, at P2, at P3, and P4, so on. So this just shows that because we have this sloping potentiometric surface, we have a lateral pressure gradient within the aquifer. Now let's look at pressures in a hydrostatic aquifer. If we drill a number of wells into a hydrostatic aquifer, and I've simulated 6 wells in this example, we see that all of the pressures lay on a single line, and the gradient in that line is controlled by the density of the water in the aquifer. But everywhere we encounter this aquifer, it will have the same pressure at a constant depth. If we then intersect this aquifer pressure line with some oil pressures, I'm going to add a couple of wells here that encounter an oil accumulation. And here we see pressures in the oil accumulation that are moving a little bit off the water pressure trend line because the density of the oil is different than the density of the water. If I blow this up, I see the oil gradient and I see the water gradient, and at the contact, the pressure of the two fluids has to be the same. In this case, well number 7 drilled the oil-water contact, so we know the depth of the oil-water contact for this accumulation. But one of the beauties of working with pressure data is that we don't actually need to drill the contact in order to know the depth of the oil-water contact. So here I'm going to kind of hide the data from well number 7. We see the pressure trend in the oil in well number 8, and we can project that down until it intersects the water pressure line, and we know the depth of the oil-water contact. So that's for a hydrostatic aquifer. Let's look at a hydrodynamic aquifer then. Here are pressures in 2 wells in a hydrodynamic aquifer. In this case, the pressure in well number 1 is higher at a given depth than the pressure in well number 2. So we have a lateral pressure gradient in the hydrodynamic aquifer. What happens when we intersect this with a constant pressure gradient in an oil accumulation? And here we have the pressure gradient in the oil being the same everywhere in the accumulation, and it intersects the pressure in the higher pressure well at a shallower depth than it intersects the pressure in a lower pressure well. So if you have a lateral pressure gradient in your aquifer and a constant oil gradient where all of the pressures lay on a single line, you have to have different oil-water contacts at the different pressure points in the aquifer. So this is why you have a differences in contacts at different points around a reservoir when you have a hydrodynamic aquifer. So here we have our cartoon of an onshore hydrodynamic aquifer, and you notice that we have inclined oil-water contacts in this aquifer. Here's a cartoon that shows the same thing we've just been talking about from a paper by Dennis and others, published in 2000. We look at a hydrostatic aquifer. We see horizontal contacts. We see the gas cap is centered on top of the oil leg. The oil-water contact is at a constant depth all the way around the structure. And if we look at the pressure, we see a gas pressure gradient, an oil pressure gradient, and then a constant water pressure gradient that is seen in all 3 of our wells, wells A, B, and C. This is very different from our hydrodynamic aquifer. Here in our cartoon, we have a tilted contact. We have the oil that is displaced away from the gas cap so that the 2 no longer directly overlay each other. Well C, which is drilled in structural closure, is no longer in hydrodynamic closure. So this is a well that would have been productive if drilled into a hydrostatic accumulation, but now it is a dry hole because the aquifer is dynamic. If we look down at our pressure trend, here's well C. It never sees the pressures in the gas cap and the oil leg because it's no longer in hydrodynamic closure. Well B encounters the oil leg at a shallower depth than the lower pressure well A. So we see the differences in the contact between well B and well A. It is inclined toward well A. I want to blow this little part of the figure up and look at it a little more closely because it's got a couple of interesting features. Here we have a situation where the oil accumulation has been shifted and is no longer directly underneath the gas cap. So here we have gas lying on oil, gas lying on oil, oil lying on water, and over here we go directly from the gas cap into the aquifer and never see the oil leg. Our oil water contact is steeply dipping in this case. Our gas oil contact is flat because the oil itself is in static pressure equilibrium. It's not flowing. And we see a slightly tilted gas water contact. The difference in the inclination between these two contacts, the oil water contact and the gas water contact, is because of the differences in the density of the gas versus the density of the oil. We can understand this if we look at Hubbard's equation, which relates the tilt on the hydrocarbon water contact to the potentiometric gradient of the aquifer. These two are related by a factor, which is the density of the water, divided by the difference in the density of the water from the density of the hydrocarbons. If we look at this factor a little more carefully, we see that if the density of the hydrocarbons approaches the density of the water, this denominator becomes very small, the correction factor becomes very large, and the tilt on the contact is much greater for a constant potentiometric gradient. If the density of the hydrocarbons is very low, then the denominator is very close to the numerator. This number is small or close to 1, and the potentiometric gradient is closer to the tilt on the hydrocarbon water contact. So what are some expected potentiometric gradients? Before I get to that, I wanted to mention that obviously from our discussion, lower density hydrocarbons have less tilt, but you also notice that in this equation, there is no term for flow rate or permeability or porosity. That's because the tilt on the contact is not controlled by the flow rate or the permeability of the reservoir or the porosity of the reservoir. It's a function of the potentiometric gradient of the aquifer and the difference in densities between the hydrocarbons and the formation water. So now let's look at the scale of the potentiometric gradient. Here we have our onshore hydrodynamic aquifer, and we see that the difference in elevation between the discharge area and the recharge area is our dH, and the distance between those two is our dx. So that's what's going to control our potentiometric gradient. Hubbard gave us some information for intermontane basins where he said that gradients can frequently be 100 feet per mile. For the U.S. Great Plains, the gradient is much less. It's 10 to 20 feet per mile. For the U.S. Gulf Coast, it is 2 to 3 feet per mile. So what do these potentiometric gradients mean in terms of tilt for hydrocarbon water contacts. They're different for oil or for gas. Gas usually has a correction factor of about 2. The tilt on the gas water contact is about twice the potentiometric gradient. And oil is commonly 7 to 15 times the factor to relate the potentiometric gradient to the tilt on the contact. So for an intermontane basin that had 100 feet per mile potentiometric gradient, you could expect to see oil water contacts that are tilted somewhere between 700 and 1,500 feet per mile. So if you have an accumulation that covers one section in the U.S., 640 acres, 1 mile from side to side, the contact on one side could be 1,500 feet higher than the contact a mile away. That's a big difference. For a gas accumulation, you would have about 200 feet of tilt in an intermontane basin, which is still very, very considerable. On the U.S. Great Plains, you have tilts of 70 to 300 feet for oil water contacts, 20 to 40 feet for gas water contacts. And on the U.S. Gulf Coast, you would have tilts on oil water contacts of 14 to 45 feet and 4 to 6 feet for gas contacts. So our gas contacts, the tilt is pretty much within depth measurement error, but we still see some significant tilts on oil contacts in the Gulf Coast. Here is an example from the Bighorn Basin, which is kind of an intermontane basin, Franny Field, and here we have an oil water contact that's tilted about 600 feet per mile. This is a standard U.S. section, so that's 1 mile from side to side, and you have about 600 feet of tilt, a very significant tilt to this oil water contact. One of the interesting things about hydrodynamic situations is you don't actually need to have structural closure in order to have a hydrocarbon accumulation in a hydrodynamic situation. Here is an example that Hubbard shows where you have just a flattening of the structure, but because the hydrodynamics tilt the oil water contact, you can have a significant accumulation even though you don't have structural closure. And here is viewing that in map view. We have a nose that is dipping into the basin. These are your structural contours right here. You'll notice that they spread out a little bit, so you kind of flattened your dip at this point. But because we have hydrodynamic flow down this nose, we have a trap even though we do not have structural closure. And here is an example from real life that shows this. This is wheat field in the Delaware Basin, Loving County, Texas. We're going to look at a cross-section across this accumulation. And here in our cross-section, we see that we do not have structural closure, even though we have over 100 feet of oil column. So we have difference in oil water contact of almost 150 feet between these two wells, but no structural closure. It is important to recognize that hydrodynamic aquifers are not limited to the onshore, but they can occur in the offshore as well. Here we have a hydrostatic aquifer offshore. We have sedimentation, which is compacting the reservoir, causing the pressure to rise. We have compaction on the bounding shales, which are causing the shales to dewater, and the water's going into the reservoir, and this is causing the pressure in the reservoir to increase. But because this is a sealed compartment, it is overpressured, but it is in static equilibrium. Contrast that with the case where we have a leak point in that aquifer. Here we still have sedimentation compacting the reservoir, dewatering the shales, raising the pressure in the aquifer. But now we have a leak point that allows the fluid to flow from where the overpressure is being generated to where the higher pressures are leaking out. And now we have a hydrodynamic aquifer. We can see these very well in some cases in the North Sea. Here we have some pressure information that Dennis and his coworkers put together for the chalk in the central Graben of the North Sea, and here we see the pressures decreasing as we go to the southeast. These contour lines are the pressure at 7,000 feet in the chalk, and therefore this is the direction to the southeast, is the direction of our hydrodynamic flow through the chalk. We can look at a large field, Valhall, Hod, here in the central Graben, and we can see the impact of this hydrodynamic flow through the chalk. Here are two maps. One map assumes a hydrostatic condition and horizontal contacts, where we have a separate accumulation at Valhall and a couple of small accumulations at Hod, and then a syncline between Valhall and Hod. If we look at this underlying cross-section, if we had a flat oil-water contact, we would have an accumulation here at Valhall, another accumulation here at Hod. We have the saddle between these two accumulations. What drilling showed was we actually have a hydrodynamic situation, and we have a significant dip on the oil-water contact. So this is all one accumulation. It's significantly larger than it would have been had it been a hydrostatic situation. And you have about 7 psi per kilometer pressure gradient in the chalks here. And that equates to a dip of just less than 1 degree, or about 15 meters per kilometer, or 80 feet per mile. Another example from Dennis and coworkers was Perched Field in the North Sea. Perched Field is a Forties field. The Forties is a Paleocene sandstone, in the North Sea. And we have two piercement salt domes associated with Perched Field, North Pierce and South Pierce. If we look at a map view of the Paleocene sands, there the pressure is moving toward the lower pressure in the northwest, but on the flanks of the central Graben, we actually have an east-west pressure gradient at Perched Field. So the hydrodynamic flow is going to be from east to west at Perched Field. Here's our map at Perched Field. We have two separate gas caps associated with these piercement salt domes. We have a single oil accumulation, and these contour lines are actually the depth of the oil-water contact in this accumulation. Now, Perched took about 25 years to go from discovery to production. And part of that was because they kept drilling dry holes on the east and south flank of the field at elevations where they thought they should have hydrocarbons. And they had a number of wells that had different oil-water contacts, and so they felt that they had a very compartmentalized field here at Perched. And when you have a highly compartmentalized field, you need a lot more wells to develop it than if you have a well-connected field. So they delayed their development until they discovered that they really had a hydrodynamic accumulation here, that all of the oil was in pressure communication. You had the two separate gas caps, but you had a tilt of about 90 meters per kilometer on the oil-water contact, because you had a pressure gradient of about 45 psi per kilometer, as opposed to the 7 psi at Valhall. This just shows you pressure data from that field. We have the two different separate gas caps. We have a single oil accumulation. All the wells encountered oil on this trend line, but different wells found different aquifer pressures depending on whether they were the east or the center or the west of the accumulation. So higher pressures to the east, shallower oil water contacts, lower pressures as you went to the west, and deeper contacts. All of these are overpressured. This shows you the normal pressure line over here. So this is pressure increasing here and depth increasing in that direction. Do we have a similar situation in the Gulf of Mexico? I don't know. I haven't seen convincing data that says we have tilted oil water contacts. I have had coworkers who I respect tell me that they have encountered tilted contacts in the offshore. This is a situation in southern Green Canyon where you have some early Miocene sands. It's an amalgamated basin floor fan. It's a very large basin floor fan. You have a number of large accumulations in these sands. K2 Timon, Shenzi, Atlantis, Mad Dog are all large accumulations. But at Green Knoll, you have a piercement salt structure, which would provide a potential leak point for these early Miocene sands. So do we have a hydrodynamic situation where Shenzi, Atlantis, and Mad Dog have tilted oil water contacts? I don't know. I wasn't thinking about that when I worked Mad Dog and Atlantis, so I haven't really studied the pressure gradient data here for the aquifer, but it certainly is suggestive that you could have a hydrodynamic aquifer. To sum up this talk, for perched water, perched water occurs in closed lows on the base of the reservoir. The greatest potential impact on the business is if you encounter it in an early well, and you have to determine whether that is the field hydrocarbon water contact or a perched contact. Usually it doesn't have a lot of impact on your hydrocarbons in place once you have developed the field, but it can have an impact on your perforation decisions. For tilted oil water contacts, they occur in hydrodynamic aquifers. The tilt is caused by a lateral pressure gradient in the aquifer. Oil water contacts are more steeply tilted than our gas water contacts. And tilted hydrocarbon water contacts can occur both onshore and offshore. So that is the conclusion of my talk. Are there any questions?
Thanks, Jim. We have received some questions from our audience. Talk about the impact of the drive mechanism, gravity drainage or active water drive. How does that impact perched water?
Well, it would not impact perched water. It would impact the perforation decisions. If you have gravity drainage, then even if you have a well that penetrates the field oil water contact, you can perf all the way down to the contact, because If you don't have any aquifer drive, you're not going to have an influx of water into your perforations. If you do have a moderate to strong water drive, however, you probably don't want to put perforations right down around the field contact, because that just asks for water coming in early, restricting your oil production. You have to handle the produced water earlier than you otherwise would. But if it's a perched contact, even though you have a field with a strong water drive, you can perforate all the way down to the perched contact.
Thank you. So should we expect to find perched water and tilted contacts in conventional and unconventional reservoirs? And what about carbonate versus clastic reservoirs?
Let me take the latter first, Susan. It doesn't matter whether you're talking about a carbonate reservoir or a clastic reservoir. In conventional reservoirs, the two behave the same. You can have a tilted contact in a carbonate reservoir every bit as easily as you can have it in a siloclastic reservoir. The unconventionals, you should still have tilted contacts, because the permeability of your reservoir doesn't really matter if you've got a pressure gradient. It's much more difficult to see contacts in unconventional reservoirs because the contact is more impacted by the petrophysical characteristics of the reservoir, but you should still have tilted contacts. Perched contacts you should still also have, but I would think that they would be of minimal importance.
Thank you. You mentioned M. King Hubbard. Is he the same Hubbard of peak oil fame?
That is indeed the same geoscientist. Very, very bright geoscientist, and he made some very significant contributions to the industry, both in his thoughts on peak oil and his thoughts on tilted hydrocarbon-water contacts.
Thank you. Those are all the questions that we have today. So I'd like to thank our audience for attending today's webinar. Later today, you'll receive a link to the recording of today's webinar, an evaluation form, and a link to register for Applied Subsurface Geological Mapping, which is scheduled December 7th through 11th at SCA's Houston Training Center. Thanks for joining us today. Goodbye.